Okay, hello and welcome to this short video on confidence intervals. We are going to start out our discussion of confidence intervals by reviewing or perhaps introducing the central limit theorem and the law of large numbers. With these two results, the use of confidence intervals becomes much more intuitive. So the central limit theorem states that the mean, we denote this using x bar, of a sample of independent, identically distributed random variables. We denote this sample as x, and our sample size is n, with a well-defined expected value, that is, there is a population average, mu, and it will have a standard deviation of sigma. So this is the mean here, and this will be approximately normally distributed when n is sufficiently large. So if this is big enough, then it will be normally distributed. It will be centered at mu, and it will have a standard deviation of sigma divided by the square root of n. Now this is a really nice result because we can sample any old distribution, no matter how non-normal it looks, and the sample mean will be normally distributed. This is a really nice result. It has great statistical properties, and it allows us to easily calculate p-values and confidence intervals. So let's go ahead and try it out. Test this theorem. Here we have a distribution of a coin toss. We have a 50% chance of getting heads and a 50% chance of getting tails. This is about as far from a normal distribution as we could possibly get, right? It's no bell curve there at all. According to the central limit theorem, if we toss 30 coins and measure the average number of heads, then the distribution of the mean number of heads will be normally distributed, or it will be normal. The probability of getting heads is 0.5, so the expected value of the mean number of heads is also going to be 0.5. The variance of the distribution of the coin toss is 0.5 squared, which is 0.25, and the variance of our sampling distribution should be the square root of 0.25 over the square root of 30. Since we're tossing 30 coins, we'll be dividing by the square root of 30. Now, the solid line here represents the theoretical normal distribution that our sample should follow. Should come from. It is centered at 0.5, and the standard deviation is the square root of 0.25 over the square root of n. Now the dashed line is the probability density of 500 trials. So for each trial, I tossed a coin 30 times. Well, I had my computer simulate 30 coin tosses anyway, and we divided the total number of heads by 30. We did this 500 times. Out of the 500 trials I performed this way, most of them ended up pretty near 0.5. That's why it's got this nice peak there. And amazingly, their spread around 0.5 nearly exactly matches the theoretical distribution. So they have the same variance, the same standard deviation. Pretty awesome. Now here's another example. This is a fun distribution. It's a bimodal distribution, so it's a mixture of two normal distributions. We're going to take 30 samples again and repeat this 500 times. So here's our theoretical distribution that is centered about the mean and has this standard deviation based on our sample size and the standard deviation of the underlying distribution. We do this 500 times, and again, remarkably, we get something, the density of our sample looks just very similar to the theoretical distribution. Now let's move on to the law of large numbers. This is something that you may have already guessed. It's a very intuitive result. When we make observations and calculate a sample mean, represented again by x bar, the law of large numbers states that our sample mean, x bar, will converge to the true population mean as our sample increases, as our sample size increases. Now, of course, this assumes that we've sampled correctly. In other words, if we take independent samples from our target population, the larger the sample is, the closer it will be to the true population mean. Again, we can simulate this in R. Here we are taking samples from a standard normal distribution. The first sample looks like it is just below 0. The second one results in a mean of just over 1. The third sample, when we take the mean of all 3 samples, gives us an average of about slightly less than 0.75. Now, as we continue to gather samples, we can see that the mean continually gets closer to 0. Now, this is on a log scale here, so as we move out here, we're taking lots of samples, and by the time we get out to the end here, we're at about 100,000 samples. And when we get way out there, close to 100,000, our estimates are virtually on top of that line at 0. It's still variable, wobbling around here and there, up and down, but in general, that trend is that it's getting closer to the true population mean, 0. Again, this is probably not a surprising result. We intuitively assume that if we collect more data, our estimates will be more accurate. But the law of large number adds some mathematical rigor to our intuition. So when we put the central limit together with the law of large number, we get this very nice result. Here on the left, we have the underlying distribution of x. This is, again, a standard normal distribution. On the right, we have the sampling distribution of the sample mean, given a couple different sample sizes. As the sample size increases, the variance around the expected value of x, which is close to 0 in this case, gets smaller. So we expect that our sample is going to be closer to 0 if we collect more samples. Again, we intuitively feel that this ought to be the case, and this tells us that it is. Because we can control the sample size, we can also control how accurate our estimate is going to be. So when you take 50 standard normal samples and you take the mean of that, you're going to get something that follows this distribution here. That's exciting. Now, the probability of getting something out here around 1, if you take the mean of 50 samples, is actually going to be about 8 times 10 to the minus 13. So that's a probability of 0.000000000008, which is a very small number. And if our sample size is 10, we're still unlikely to get a sample mean of over 1. You see this drops off. It's very close to 0 here. But the probability is more like 0.0008. In either case, we are much, much more likely to get a sample mean that is closer to 0 than it is to 1. Now, 95% of the samples that we're collect are going to fall within plus or minus 1.96 times the standard deviation of the mean. This forms the basis of our confidence interval. And as a side note, the area under this curve, if we calculate the area under the curve, it's going to be equal to 1 for all distributions. So the value 1.96 here is found by looking for the critical value where this area is equal to 0.96. So that's a probability, it measures the probability that our sample is going to fall in this region. So the height of the curve is a measure of the likelihood that we will observe a value at that location. And then the area is the probability that we'll observe a value from that distribution within that shaded region. So when the sample size is 10, the distribution of x bar looks like this. So this is the same scale down here, and we see that the variance is smaller. The y scale is not the same, but the x scale is. So the width of this interval is much smaller than it is on the previous screen because we have a smaller standard error for our estimate. The estimated mean is going to fall within mu plus or minus 1.96 times sigma over the square root of n. So the probability that it falls in that region is 0.95. We get this distribution from the central limit theorem, and we can measure that probability using this distribution. Now from this, we infer that if we collect a sample, and all we have is the sample mean, we don't have the true population mean, we can infer that the true population mean lies inside this interval here, which is our confidence interval. So it's the mean of x bar, plus or minus 1.96 times the standard deviation, and we estimate the standard deviation from our sample, because we don't know sigma necessarily, and we divide that by the square root of n. So the probability that this confidence interval overlaps the true population mean is 0.95. And that is essentially how our confidence intervals are defined. So let's say that we are studying a population and we have a sample of 100 systolic blood pressure samples. Our sample mean is 123 and our sample standard deviation is 12. What is our confidence interval? So the standard error of our estimate is defined here. That's 12 over the square root of 100. 12 is the standard deviation that we measured from our sample, and then the standard error is going to be the standard deviation of our sample mean, but to avoid using that term too much, we call this the standard error. That is a measure of how much we expect our sample mean to vary. So we calculated the 95% confidence interval is 123 plus or minus 1.96 times 12 over the square root of 100, which is 10. And that is approximately 120.66 to 125.34. Yay! Now, let's go ahead and simulate a sample from this distribution in R. We're going to use the CI function from the gmodels package to do this. So let's go ahead and set a random seed for the random number generator so we can get a consistent result each time. And then we are going to create a random normal sample with 100 observations with a mean of 123 and a standard deviation of 12. We pass that with the pipe to the CI function, and it gives us a confidence interval. So our estimate is 124 with confidence interval from 121.6 to 126.4. And that, again, is very similar to what we calculated up here. Not exactly the same because each sample is going to be a little bit different. And we also see the standard error is nearly identical to the standard error up here. That'd be 12 divided by the square root of 100, which is 10. So 1.2 would be what we would expect the standard error to be. So again, very close. Now let's do this another 100 times. We're going to assume that the true mean is actually 123. And here we see all of our estimates with their corresponding confidence intervals. Those with 95% confidence intervals that contain the true mean is represented by this vertical line here. Those with confidence intervals that contain the true mean are going to be colored black, and those that do not contain the true mean are colored orange. We also have these two dashed lines on either side representing the region where we expect 95% of our estimates to land. We don't quite have 95% of our confidence intervals that contain the true mean, but it's very close. Again, there's always going to be some variability when we do these simulations, but it should be close to 95%. In this case, we're at 94%. Also, it should come as no surprise that all the estimates that are outside of the 95% confidence region have confidence intervals that do not contain the true mean. So these confidence intervals do not contain that true mean there. There's a one-to-one correlation between these two. If you're outside of this region, you're probably not going to have an estimate that overlaps the true population mean. So here we have a data set expanding on this blood pressure example. We are showing some simulated individuals who are at risk of hypertension. We have blood pressure on the y-axis, age on the x-axis, and individuals who are taking beta blockers are colored orange. When we look at the model results, we're going to fit a statistical model to this. And when we look at the model results, we see that all of the coefficients are statistically significant. We also note that this value here is very close to this value here. So those are going to cancel out. And that shouldn't be too surprising. If we look back at this line here, we kind of guess that this line is going to be very close to 0, if not equal to 0. So those on beta blockers have a fairly consistent blood pressure, irregardless of age. So we can use these results here to look at the individual betas or the coefficients, but it doesn't tell us what that slope for that line is going to be, which is going to be a combination of those two. So let's go ahead. We already saw from before what the CI function will do. Now our model is called LM0, and we're going to leave off the fourth column because it's not important. It runs off the edge of the page. This will give us estimates for each of the betas here, each of our coefficients, and it will give us a confidence interval along with a p-value for those estimates. But what we really want is not the not necessarily the slope for the untreated group, but we want the slope for the treated group. And that is going to be equal to age plus this interaction term, age by beta. So another useful function to do this is the estimable function. It's also from the gmodels package. And we just need to supply it with our linear model and the values for the coefficients. So if we want to estimate the slope of the beta blocker group, we do not want the intercept, so that will be 0. We do want the slope for the untreated group. We do not want the difference in intercept for the beta group. And we do want the difference between the slope in the beta group and the slope in the untreated group. So we're going to add those two together. Going to calculate a confidence interval. Again, we're going to rearrange the output and drop a few columns. And we get our estimate is 0.04 with a confidence interval of negative 0.66 to 0.73. This estimate's very close to 0. The confidence interval contains 0 in it, and our p-value is fairly high. So all of those things together confirm and are related to each other, but they're all telling us that the slope of this line here is not statistically different from 0. So another nice use of the estimable function is to calculate confidence intervals for predicted estimates. For example, what is the average blood pressure among untreated 52-year-old individuals? Again, we can put our data into estimable. We have our linear model. We are predicting for an individual. So we include the intercept. The individual is 52 years of age, so we put 52 in for this value here. And because they are untreated, these two coefficients are going to cancel out and they will be equal to 0. We want to get our 95% confidence interval. We're going to select a couple of columns that we actually want. Our estimate for untreated hypothetical individual of 52 years of age in our target population who is at risk of hypertension is going to be 146.6. And our confidence interval for that estimate is 142.0 up to 151.2. So there we have it. Very nice use of estimable. It's a nice function. Will give you lots of great, powerful results. That's all we have for today. Hopefully you have found this helpful and maybe you've learned something. Thanks.